Welcome to this problem walkthrough. In this session, we'll explore problem number 860, Lemonade Change, a fascinating challenge that tests your ability to manage transactions efficiently. Get ready to dive into the details, discuss potential approaches, and refine your problem-solving skills. Let's get started. In this problem, you are running a lemonade stand where each glass of lemonade is sold for $5. Customers come to you in a queue, and each customer pays with either a $5, $10, or $20 bill. Your task is to provide the exact change to every customer at the time of their purchase. Importantly, you start the day with no money at all. This means you don't have any cash on hand initially to give change. Your goal is to determine if it's possible to provide the correct change to all customers in the given order. The input to the problem is a list, called bills, where each element represents the bill a customer pays with. The length of the list can range from 1 to 10,000, and the values within the list are restricted to $5, $10, or $20 bills. The output is a Boolean value. Return true if you can give the correct change to every customer and false if at any point you cannot provide the necessary change. Let's start with the first example. Here, the input is bills equals 5, 5, 5, 10, 20. The output is true, and here's why. The first customer pays with a $5 bill, so no change is needed, and you now have one $5 bill in your possession. The second customer also pays with a $5 bill, so again, no change is needed, and you now have two $5 bills. The third customer follows the same pattern, paying with a $5 bill, and you now have three $5 bills. The fourth customer, however, pays with a $10 bill. To provide the correct change, you give them one $5 bill and keep their $10 bill, leaving you with two $5 bills and one $10 bill. Finally, the fifth customer pays with a $20 bill. For this transaction, you give $15 as change, one $10 bill and one $5 bill, and keep the $20 bill. After all the transactions, you are left with one $5 bill, and you successfully provided change to all customers. Therefore, the output is true. Now, consider the second example, where the input is bills equals 5, 5, 10, 10, 20. The output here is false. Let's break this down. The first customer pays with a $5 bill, so no change is needed, and you now have one $5 bill. The second customer also pays with a $5 bill, so you now have two $5 bills. The third customer pays with a $10 bill, so you give them one $5 bill as change and keep the $10 bill, leaving you with one $5 bill and one $10 bill. The fourth customer also pays with a $10 bill. To provide the correct change, you give them your remaining $5 bill and keep their $10 bill. Now, you have no $5 bills left and two $10 bills. When the fifth customer pays with a $20 bill, you need to provide $15 as change, but since you don't have any $5 bills left, it's impossible to give the correct change. Therefore, the output is false. Now, let's take a look at the third example, where the input is bills equals 5, 5, 5, 5, 20, 20, 20. The output here is also false. Here's the breakdown. The first four customers each pay with a $5 bill, so no change is needed for these transactions, and you now have four $5 bills. The fifth customer pays with a $20 bill. To provide the correct change, you give them $15, one $10 bill and one $5 bill, and keep their $20 bill. You now have three $5 bills left. The sixth customer also pays with a $20 bill. Again, you provide $15 as change, one $10 bill and one $5 bill, and keep their $20 bill. Now, you are left with two $5 bills. Finally, the seventh customer pays with a $20 bill. This time, you need to provide $15 as change, but with only two $5 bills available, it's not possible to give the correct amount. As a result, you cannot provide change to this final customer, and the output is false. This example highlights an important aspect of the problem. You must carefully manage the cash you receive and prioritize using larger bills, like $10, for change whenever possible. The constraints ensure that the problem is computationally feasible. Specifically, the number of customers in the queue can go up to 10,000, so your solution must be efficient enough to handle this upper limit. Each bill in the bills array will always be one of 5, 10, 20, and you must provide exact change for each transaction or immediately return false if it's not possible. Additionally, edge cases include scenarios like having only one transaction, such as when the input is bills equals 5, where the output is true since no change is needed, or bills equals 10, where the output is false because you cannot provide $5 as change. Other cases involve repeated exact change requirements, such as bills equals 5, 10, 5, 20, 5, 20, where you eventually run out of $5 bills, making it impossible to give change. Finally, the problem expects you to handle large input sizes efficiently, ensuring your solution can process up to 10,000 transactions without performance issues. By keeping these constraints and examples in mind, you'll be able to approach the problem systematically and develop a robust solution. To begin, let's look at the brute force approach. The intuition here is to simulate every transaction by keeping track of all the bills we've received and attempting to find combinations to provide exact change for each customer. For example, if a customer pays with a $20 bill, we would search through all the bills we've collected so far to see if we can form the $15 needed for change. While this might seem like a straightforward way to solve the problem, the issue lies in its inefficiency. Searching for combinations of bills means iterating through all the stored bills for every transaction, which is computationally expensive. This results in a time complexity of O(n*k), where k is the number of bills we have at any given time, and a space complexity of O(k) to store these bills. Given the fixed denominations of $5, $10, and $20 in this problem, this approach is overly complex and unnecessary, which is why it's not a practical solution. Now, let's consider the greedy approach, which provides a more optimized solution. The key idea here is to always give change using the highest denominations available. This ensures that we minimize leftover bills and maintain flexibility for future transactions. Here are some critical observations. Since the bills involved are limited to $5, $10, and $20, we only need to manage change for $10 and $20 bills. Specifically, a $20 bill requires $15 as change, which can be given as $10 and $5 or three $5 bills, while a $10 bill only requires $5 as change. To implement this strategy, we use two counters, 5 and 10, to track the number of $5 and $10 bills we have. For every customer, if they pay with $5, we simply increment the 5 counter. If they pay with $10, we decrement 5 to give $5 as change and increment 10. For a $20 bill, we prioritize using one $10 and one $5 if possible, or three $5 bills if not. If at any point we cannot provide the required change, the function returns false. This approach is highly efficient, with a time complexity of O(n), as each transaction is processed once, and a space complexity of O(1), since we only use two counters. It's a simple and effective solution that leverages the constraints of the problem. The greedy approach is the strategy we've chosen, and here's why. First, it's highly efficient, processing each transaction in constant time, which leads to an overall time complexity of O(n). Second, it's simple, requiring only two counters without the need for complex data structures. Third, it guarantees correctness by prioritizing higher denominations for change, ensuring that future transactions are not compromised. Finally, it's scalable, as its constant space usage makes it well-suited for handling large customer queues. When comparing the brute force and greedy approaches, the brute force method's exhaustive search is computationally expensive and impractical, whereas the greedy approach is tailored to this problem's constraints, making it optimal. Although greedy algorithms can sometimes fail in problems with broader conditions, the fixed denominations and clear hierarchy of bills in this problem make it a perfect fit. Ultimately, the key takeaway is that this problem's constraints naturally align with the greedy solution, where tracking only the $5 and $10 bills is both sufficient and efficient. This makes the greedy approach the ideal choice for solving the lemonade change problem. To start, it's essential to define the problem clearly. The task involves simulating the process of a cashier handling transactions, where the goal is to determine if you can successfully provide the correct change for every customer. You'll receive a series of bills, and for each one, you must decide whether to keep it or use it to give change. The goal is to process all transactions efficiently and return a Boolean indicating success or failure. Now, to do this, you need to understand the inputs and outputs. The input is a list of bills received in the order of transactions, such as 5, 10, 20. The output is a simple Boolean, true if all transactions can be handled, and false otherwise. To implement this, you'll need to initialize data structures. A dictionary is ideal here because it allows you to track the count of each bill denomination, such as $5, $10, and $20, and perform updates and lookups in constant time. While arrays are another option, dictionaries make the implementation cleaner and more adaptable if additional denominations were introduced in the future. To process the transactions, iterate through the list of bills one by one. For each bill, there are 3 key cases to handle. First, if the bill is $5, simply increment the count of $5 bills since no change is needed. Second, if the bill is $10, check if you have a $5 bill available to give as change. If you do, decrement the count of $5 bills and increment the count of $10 bills. If you don't, return false immediately because the transaction can't be completed. Third, if the bill is $20, prioritize giving change using one $10 bill and one $5 bill. This preserves smaller denominations, which are more versatile for future transactions. If no $10 bills are available, check if you can use 3 $5 bills instead. If neither option works, return false. Once all transactions are processed without running into issues, you can return true. The key insight here is to always prioritize higher denominations for change. This strategy reduces the likelihood of running out of smaller bills later. Additionally, using a dictionary for bill counts ensures that updates and lookups are efficient, and implementing early exits when change cannot be given avoids unnecessary computation. The dictionary is the core data structure in this algorithm. It tracks the count of each bill denomination, such as $5, $10, and $20. For example, a dictionary like 5, 3, 10, 2, 20, 0 means you have 3 $5 bills, 2 $10 bills, and no $20 bills available. This structure is efficient for updating and querying because it operates in constant time. Now, let's discuss the algorithm's complexity. The time complexity is O(n), where n is the number of transactions, because each transaction is processed in constant time. The space complexity is O(1), since the dictionary is fixed in size, containing only 3 keys regardless of the number of transactions. It's also worth considering edge cases. For example, if there are no transactions, the output should simply be true since there's nothing to process. If you encounter a situation where there aren't enough bills to provide change, the algorithm ensures you return false as soon as the condition is detected, avoiding unnecessary work. Finally, for large inputs, the algorithm remains efficient due to its linear time complexity, making it well-suited for high transaction volumes. Let's walk through a couple of examples to see the algorithm in action. First, consider the input 5, 5, 5, 10, 20. Start with no bills, 5 o'clock, 10 o'clock, 20, 0. Process the first $5 bill and update to 5, 1, 10 o'clock, 20, 0. The second and third $5 bills increase the count to 5, 3, 10 o'clock, 20, 0. Now comes a $10 bill, give one $5 bill as change, leaving 5, 2, 10, 1, 20, 0. Finally, for the $20 bill, give one $10 bill and one $5 bill as change, resulting in 5, 1, 10 o'clock, 20, 0. All transactions are processed successfully, so return true. Now take another input, 5, 10, 20. Start with 5 o'clock, 10 o'clock, 20, 0. Process the $5 bill, updating to 5, 1, 10 o'clock, 20, 0. For the $10 bill, give $5 as change, leaving 5 o'clock, 10, 1, 20, 0. The $20 bill, however, requires change, but you don't have enough to provide it, so return false. These examples highlight how the algorithm dynamically adjusts the bill counts and exits early when change isn't possible. This solution efficiently handles the lemonade change problem by simulating the cashier process. We start by initializing 2 variables, 5 and 10, to count the number of $5 and $10 bills available. This is important because these denominations are the only ones we can use to provide change. We then iterate through each bill in the input list bills. For each transaction. 1. If the bill is $5, we simply increment the 5 counter since no change is required. 2. If the bill is $10, we check if we have at least one $5 bill to give as change. If we do, we decrement 5 and increment 10 to account for the new $10 bill. If no $5 bills are available, we return false as we cannot provide change. 3. If the bill is $20, we prioritize giving one $10 and one $5 as change, if we have them, because this minimizes the depletion of $5 bills. If that isn't possible, we check if we can give three $5 bills as change. If neither option is feasible, we return false since we cannot provide the required change. Finally, if all transactions are processed successfully, we return true to indicate that we were able to provide correct change for every customer. This solution has a time complexity of O(n), where n is the number of transactions, as we process each bill exactly once. The space complexity is O(1), since we use only two variables to track the counts of $5 and $10 bills. Here, we have the Java implementation of the lemonade change problem. The method takes an array of integers, bills, where each number represents the bill a customer hands over. We initialize two counters, 5count and 10count, to keep track of the number of $5 and $10 bills we have in our cash register. Then, we loop through each bill in the input array. If the customer gives a $5 bill, we simply increase 5count because no change is needed. If the customer gives a $10 bill, we check if we have at least one $5 bill to give as change. If we do, we decrement 5count and increase 10count. If not, we return false since we cannot provide change. For a $20 bill, we prioritize using one $10 bill and one $5 bill as change, reducing both counters accordingly. If that's not possible, we check if we can use three $5 bills instead. If neither option works, we return false because we cannot provide the required change. Finally, after processing all the bills, if we've managed to provide the correct change for every customer, we return true. This signifies that we successfully handled all transactions. The logic here ensures that we prioritize using larger bills as change when possible, which helps us retain smaller bills for future customers. By carefully managing our cash register with this strategy, we maximize our ability to give change in all scenarios. To begin solving the problem, let's walk through example 1 where the input bills are 5, 5, 5, 10, 20. Starting with the first customer, they pay with a $5 bill. Since no change is required, we simply accept the payment and increment our count of $5 bills. Now we have one $5 bill and no $10 bills. For the second customer, they also pay with a $5 bill. Again, no change is needed, so we accept the payment and increase our $5 count to 2. Similarly, the third customer pays with another $5 bill. We accept it, bringing our $5 count to 3, while the $10 count remains 0. Now, moving to the fourth customer in example 1, they pay with a $10 bill. Here, we need to provide $5 as change. Since we have three $5 bills available, we give one as change, decrement our $5 count to 2, and increment our $10 count to 1. Finally, the fifth customer pays with a $20 bill. To provide $15 in change, we use the preferred option of one $10 bill and one $5 bill. This reduces our $10 count to 0 and our $5 count to 1. Since we were able to give correct change to all customers, the output for this example is true. In example 2, the input bills are 5, 5, 10, 10, 20. Starting with the first customer, they pay with a $5 bill. We accept it, increasing our $5 count to 1 while our $10 count remains 0. The second customer also pays with a $5 bill, so we accept it and increment our $5 count to 2. For the third customer, they pay with a $10 bill. To give $5 as change, we decrement the $5 count to 1 and increment the $10 count to 1. For the fourth customer in example 2, they also pay with a $10 bill. Again, we need to give $5 as change. We decrement the $5 count to 0 and increase the $10 count to 2. Now, the fifth customer pays with a $20 bill, and we need to provide $15 in change. The preferred option is to give one $10 bill and one $5 bill as change, but since we have no $5 bills left, we cannot provide the correct change. Therefore, the result for this example is false, as not all customers received the correct change. Let's look at example 3, where the input bills are 5, 5, 5, 5, 20. The first customer pays with a $5 bill, which we accept, incrementing our $5 count to 1 while the $10 count remains 0. The second customer also pays with a $5 bill, so we accept it and increase our $5 count to 2. For the third customer, they again pay with a $5 bill, and we accept it, bringing our $5 count to 3. The fourth customer in example 3 pays with another $5 bill. We accept it, increasing our $5 count to 4 while the $10 count remains 0. Finally, the fifth customer pays with a $20 bill. To provide $15 in change, we use the fallback option of giving 3 $5 bills. This reduces our $5 count to 1. Since we were able to give correct change to all customers, the output for this example is true. In this problem, the time complexity is determined by how many operations the algorithm performs relative to the size of the input list, bills. The algorithm iterates over the input list one time, processing each bill sequentially. For every bill, it performs a set of constant time operations, such as checking conditions and updating the counts of $5 and $10 bills. These operations do not depend on the size of the list, they take the same amount of time regardless. Since the algorithm processes each of the n bills exactly once, the total time complexity is proportional to the number of bills, or O(n). This holds true across different scenarios. If every customer pays with a $5 bill, the algorithm only increments the 5 counter, which is still O(n). With a mix of $5, $10, and $20 bills, it remains O(n), because each bill is handled in constant time. Even in the worst case, where every customer pays with a $20 bill and the algorithm has to check both counters repeatedly, these checks are also constant time operations, keeping the overall complexity at O(n). Now that we've established that the time complexity is O(n) in all cases, let's examine the space complexity. The solution uses 2 integer variables, 5 and 10, to keep track of the counts of $5 and $10 bills. These variables require a fixed amount of memory, regardless of how many bills are in the input list. Importantly, the algorithm doesn't create any additional data structures or make a copy of the input. It processes the list bills directly, without modifying it. Because the memory usage is limited to the 2 integer counters, it remains constant no matter how large the input is. Therefore, the space complexity is O(1). This efficient use of space ensures the algorithm is optimized for memory as well as time. To understand just how efficient this solution is, let's compare it to a possible naive approach. A less optimized solution might involve storing all the bills in a dynamic list or dictionary and then repeatedly searching for combinations to give change. In this case, every time a customer pays, the algorithm would need to search for a valid combination of bills, which could take k time per customer, where k is the number of bills stored so far. Over n customers, this results in a time complexity of n*k. Additionally, storing all the bills would require O(n) space, as the memory usage grows with the number of customers. By contrast, the current solution avoids storing individual bills and eliminates the need to search for combinations altogether. Using counters for $5 and $10 bills keeps the time complexity at O(n), and the space complexity at O(1), making it significantly more efficient. Finally, let's confirm the time complexity with a simple mathematical proof. The algorithm iterates through the input list bills, which has a length of n, performing 1 iteration per bill. During each iteration, it executes a constant number of operations, such as conditional checks and variable updates. Since these operations are performed in O(1) time for each bill, the total time taken is the number of iterations, n, multiplied by the time per iteration, O(1). This gives a total time complexity of O(n). The space complexity remains O(1), as the algorithm only uses a fixed amount of memory for the 2 counters, regardless of the input size. This mathematical confirmation further reinforces the efficiency of the solution. When working on problems like lemonade change, it's important to avoid some common mistakes that can lead to incorrect results or inefficiencies. One frequent mistake is failing to consider edge cases. For instance, assuming that exact change is always possible or ignoring scenarios with large denominations can result in errors. Another issue is relying on brute force methods, where you simulate all possible combinations of transactions. This approach quickly becomes inefficient, leading to exponential time complexity, which is impractical for larger inputs. Additionally, in languages like C++ or Java, you should be cautious about integer overflow when performing calculations involving large values. Misinterpreting problem constraints is another common pitfall, such as assuming you have unlimited denominations when the problem specifies otherwise. Lastly, off-by-one errors in loops, particularly in dynamic programming implementations, can cause misaligned indices and incorrect results. Being mindful of these mistakes can save you significant debugging time and ensure your solution is robust. To excel in interviews, it's crucial to understand the problem's context. For instance, you need to clarify whether the goal is to find a single solution, all possible solutions, or simply verify feasibility. Each scenario may require a distinct approach, such as greedy algorithms for efficiency or backtracking for completeness. Scalability is another key consideration. When dealing with large inputs, focus on solutions with lower time complexities, like logarithmic or linearithmic approaches. Problems involving transactions often revolve around patterns such as dynamic programming, greedy strategies, or memoization, so recognizing these patterns can give you an edge. Finally, be prepared to explain the trade-offs of your chosen approach. For example, while a greedy algorithm may be faster, it might not handle all edge cases reliably. On the other hand, dynamic programming guarantees correctness but might consume more memory. Being able to articulate these trade-offs demonstrates your understanding and problem-solving flexibility. Exploring related problems can deepen your understanding of the techniques used in lemonade change. For instance, LeetCode 322, coin change, is a classic dynamic programming problem where the goal is to find the minimum number of coins needed to make a target amount. LeetCode 406, queue reconstruction by height, introduces a different application of the greedy approach, helping you practice decision-making under constraints. LeetCode 279, perfect squares, is another variation of the coin change problem, where you find the minimum number of perfect square numbers that sum to a given target. Lastly, LeetCode 518, coin change 2, focuses on calculating the total number of combinations to achieve a target amount, which emphasizes dynamic programming techniques. These problems highlight the versatility of patterns like dynamic programming and greedy algorithms across a range of scenarios. There are several alternative approaches to solving change-making problems, each with its own strengths and trade-offs. The greedy algorithm is often fast and intuitive, particularly when a local optimal choice leads directly to a global solution. However, it might fail in cases where a broader perspective is needed. Dynamic programming, on the other hand, guarantees correctness for most change-making problems and is especially useful when you need to account for all possibilities. Although it requires additional memory, its time complexity, usually O, n*m, where n is the target value and m is the number of denominations, makes it efficient for many scenarios. Backtracking is another approach, ideal for generating all possible solutions, but its exponential time complexity means it's better suited for smaller inputs. Finally, breadth-first search, or BFS, can be highly effective for unweighted problems where the shortest path, like the minimum number of coins, is needed. While its time complexity aligns with dynamic programming, BFS may demand more memory to handle the queue. Choosing the right approach depends on the problem's constraints and requirements. Thank you for joining me on this walkthrough of the lemonade change problem. We covered the problem's core concepts, discussed the greedy approach for managing transactions, and highlighted key takeaways to help you tackle similar challenges. Don't forget to practice and refine your skills. See you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!